Alright, so this is a review for the mole. What I'm going to do in this review is go through everything except for the mole conversions, and I'll do a separate review for mole to grams, mole to liter, etc. If you have any questions, too bad. No, if you have any questions, just email me. I'll check my email tonight. And hopefully this helps a little bit. Alright, so the first objective says, know the definition of a mole. Don't forget that a mole was based on carbon-12, and so it was concluded that in 12 grams of carbon-12 there is exactly 1 mole of particles. And thanks to Avogadro, he said that 1 mole contains 6.02 times 10 to the 23rd atoms, molecules, electrons, whatever particle or unit it is that you are talking about. Alright, so that 6.02 times 10 to the 23rd is equivalent to a mole, and again that was thanks to Avogadro. Alright, the third bullet down says determine the gram atomic mass of an element. Don't forget that if you look at the periodic table, this atomic mass number, whether it's the 7 for lithium, 9 for beryllium, 23 for sodium, again we use that rounded number to make our lives easier. That atomic mass we use in terms of the gram formula mass, and so instead of saying 7 atomic mass units, we say that there are 7 grams, and in this case this is the gram atomic mass of lithium. And this number then we can say under the inception that if we have this weighed out, this mass is going to be equivalent to 1 mole of lithium. And so in this case for lithium, if we have 7 grams of lithium measured out, we are going to have 6.02 times 10 to the 23rd lithium atoms. Again, it's this that is equivalent to 1 mole. And from class we learned that 1 mole is equivalent to the formula mass. Alright, the next bullet says using subscripts determine the number of elements in each compound. And so we'll take a look at a couple. The first one here is water. If I look at water, water has 2 hydrogens and 1 oxygen atom. If I look at something a little more complex like calcium hydroxide, I have 1 calcium, but since I have a parenthesis and the 2 outside, I'm going to multiply it through. So in this case I have 2 oxygen and 2 hydrogen. If I look at an even fancier one, maybe if I can find an example. Alright, if I look at an even fancier one, I have aluminum sulfate here. Here I have 2 aluminum. I have 3 sulfurs and 12 oxygen. So don't forget that the number outside the parentheses, you're going to distribute that number through, but again, it just goes to the thing inside the parentheses. The next bullet says recognize binary compounds. Binary means 2 types of elements only. So water is binary. NaCl, sodium chloride, is binary. Calcium hydroxide, aluminum sulfate are not because they have more than 2 atoms. 1, 2, 3, 1, 2, 3 in this case. If you look at the next bullet, determine the formula mass, gram formula mass, molecular mass, molar mass of a compound. Now, those words are all there in parentheses because they all are the same thing. Basically, all you're doing from the periodic table is just looking up the gram formula mass and then multiplying that by however many atoms you have. So if we look at water, the molar mass of hydrogen is 1 and oxygen is 16, and so the formula mass of water is 18 grams. If you look at calcium hydroxide, the formula mass of calcium is 40, Oxygen is 16 again, water is 1, and so in this case 40, if I can squeeze it in here, 32 and 2, so the formula mass of calcium hydroxide is 74 grams. And again, you can do the same for aluminum. It gets a little trickier than this. The next bullet talks about a hydrated salt. The example of the hydrated salt we did in the lab in class was copper sulfate, and this contained 5 moles of water. And so if you're going to look at the formula mass, again, you start by counting atoms. What's unique about this is that doesn't mean multiply, that just means contains or includes. So in this case, you have to distribute that 5 through, and I have 10 hydrogen and 5 oxygen. And so you just look up the masses again from the periodic table. Copper is 64, sulfur is 32, oxygen is 16, hydrogen is 1, oxygen is 16, and so, and so the formula mass if you add it up is 250 grams. Right, 250 grams. Now, if you want to know the percent of water, right, so the percent just of the water, this hydrogen and this oxygen numbers down here is what came from that water, and so that adds up to 90. So if I want to know the percent of water in this example, 90 divided by 250 times 100. And when I do that, let's see my calculator here, 90 divided by 250 is 36%. And again, doing our lab, that was our theoretical yield for the percent of water, right? We compared what we got to this actual 36 that it was supposed to be. Some of you did better than others, I know. All right. If I want a new percent composition of each individual element of the compound, what you're going to do is you're going to take the mass of each element divided by the whole. So in this case, let me get this out of the way here. In this case, if I wanted to know what percent copper made this hydrate, I would take 64 divided by 250 times 100. If I wanted to know what percent sulfur made of this compound, it would be 32 divided by 250 times 100. If I want to look at something a little easier, let's look at sodium chloride. It's a salt. All right, 1 sodium, 1 chlorine. So I have a formula mass of 58, and if I want to know what percent sodium makes up of this 58 grams, I'm going to take 23 divided by 58 and then times 100. So in this case, sodium makes up 39.66%. Chlorine then makes up 35 divided by 58 times 100. And in this case, 35 divided by 58, this is 60.34. Now, one thing to keep in mind is that 39% and 60%, when you add them up, it should give you 100%. And 39.66 plus 60.34 adds up to 100. Alright, the next bullet talks about the percent of water in a hydrate. Now, we did that on the last slide, and you could see that here we figured out, right, the percent of water. And again, we did that by looking at this down here. Well, in our lab, we weren't given the formulas, we were measuring in grams. And so let me show you an example as if you had masses from a lab. Alright, so if this is our hydrate, when we heat it up, remember, it turned into our hydrate. And what we lost was our 5 moles of water. So when we heated this up, we lost water and it turned into our anhydrate, and it's our salt without the water. So if we started, let's say, with 10 grams of copper sulfate, and when we were done heating that, let's say this weighed 6.4 grams, how much water did we lose? Well, remember the law of conservation of mass from the last unit, right? Our products, the water and the copper sulfate, have to add up to the 10 grams. Or we talked about it in the lab, saying that our hydrate minus our anhydrate is going to be our water loss. So in this case, 10 minus 6.4 grams gives me a water loss of 3.6 grams. And so if I want to know the percent of water, I'm going to take my 3.6 grams, that's my water lost, divided by 10, and then multiply by 100. And so the percent of my water loss was 36%. So if you were in my lab group, it was supposed to be 36%. We just looked at it before. We did a perfect job. All right, but again, you just look at your hydrate, what you started with, subtract your anhydrate, what you ended with, and then that's your water that was lost. And again, you're going to take then this part, that's the water, divided by the whole, which was your hydrated salt to begin with, your 10 grams. The last thing we're going to look at, oh, no, not the last thing. The next bullet, it talks about determine the number of atoms of each element in a formula when the formula is preceded by a coefficient. So let's take a look at this 5H2O. 5H2O tells me that I have 10 hydrogen atoms and 5 oxygen atoms. Now I can look at it macroscopically, so I can say that I have 10 moles of hydrogen atoms and 5 moles of oxygen atoms, or I can look at it microscopically and just say I have 10 hydrogen atoms and 5 oxygen atoms. The 5 in the front then can kind of be the same thing. I can say that I have 5 moles of water, or I can say that I have 5 molecules of water. So this idea of molecules and atoms, this is microscopic, really, really small scale. Moles is talking in terms of 6.02 times 10 to the 23rd of these atoms, and this is 5 times that. So these are macroscopic, huge scales when we talk about moles, but it's still the same number. And so if I have something like my copper sulfate, and instead of having 1 mole of copper sulfate, I say that I have 3 moles of that copper sulfate, what I really have is 3 moles of copper sulfate and 15 moles of water. So that 3 gets distributed through. All right, so any coefficient that's in front, everything gets multiplied by that 3. All right, not just the copper sulfate, but the water as well. All right, so this was subscripts, coefficients can refer to atoms or mole ratios. That's what we just did on this last slide. Given the formula of a compound, determine the number of moles of each element. So again, that's talking about 10 moles versus 5 moles. And the bottom thing, again, we're going to have a slide, a whole different review thing for the conversions. The last thing is talking about is empirical versus molecular formulas. So we'll go over that quick. Alright, so the empirical formula is the most reduced formula. You're going to learn later on this year that all ionic compounds are listed in their empirical formula, and some covalent compounds are, but oftentimes we give more information. We give all of the molecules. So empirical formula is the most reduced. So if you take a look at NaCl and CH4, I can't reduce these any further. But something like C2H8, both of these numbers can be divided by 2, and so I can reduce that to CH4. So then my empirical formula. So what we call this one that can be reduced is the molecular formula. And so in any given word problem, I can be given a molecular mass. So let's say I have a molecular mass of 84. And my empirical formula is CH2. From this empirical formula, I can figure out its formula mass. So its formula mass is 14 grams, but what they're telling me is that the mass of the whole molecule is 84. So if I take 84 divided by 14, I get 6. So this 6 is telling me that I need to multiply my empirical formula by 6. And so really what you're doing is multiplying the subscripts by 6. And so here, this is my molecular formula. Alright, now sometimes if I have something like 46 grams of NO2, again, this is my molecular mass, the mass of the whole molecule. Molecular is not spelled right, don't judge me. Sometimes when I'm given the molecular mass and I figure out the formula mass, I find that they're the exact same number. So in this case, because they're the same number, this empirical formula is also the molecular formula. So the empirical formula can be the molecular formula, but you have to know the masses first. And if the molecular mass matches the formula mass, then you don't need to multiply by anything else. If instead it was 46, let's say it was 92 for the molecular mass, well, 92 divided by 46 would give me 2. So what I would have for a molecular mass is N2O4. Alright, so hopefully that helped.